Hello. Find the equation of the tangent to the curve x squared at 5x minus 2, where the curve cuts the line x equal to 4. If you're stuck, what you can get started with is writing that y is equal to x squared at 5x minus 2. And if it cuts the line at x equal to 4, you can find the y coordinate. So at x equal to 4, y is equal to 4 squared at 5 times 4 minus 2. And this will get you started. You got your y coordinate 30, which is 34. The gradient at x equal to 4 is the value of dy dx when x equals 4. So if you find dy dx, so we know that y is equal to x squared at 5x minus 2, so dy dx, we differentiate this, will give us 2x at 5. So when x is equal to 4, the gradient of the curve at x equal to 4 dy dx is now equal to 2 times 4 at 5, which is 13. So we know our gradient is 13 when x is equal to 4. And further to that, we can go ahead now and find the equation of the tangent. We use this familiar equation. And we substitute here y. Let's just write it over here, which is y minus 34 equal to 13 brackets x minus 4, which you can rearrange to write as 13x minus y minus 18 is equal to 0. So this is the equation of the tangent to the curve x squared at 5x minus 2, where the curve cuts the line x equal to 4. Thanks for watching. My name is Alistair. Bye for now. So here's our next complex number. We'll clear the brackets, simplify what cosine pi over 3 is and sine pi over 3. Cosine pi over 3, incidentally, is a half, and sine pi over 3 is root 3 over 2. So we have root 3 over 2i, and we'll clear the brackets here to give us 1 add root 3i. The modulus of this, 1 add root 3i, oops, it's a straight line, is equal to 1 squared add root 3 squared. And we take the square root of all this to give us 2. The argument, the principal argument, a lowercase arg is equal of 1 add root 3i is equal to tan inverse of root 3 over 1. Which gives us pi over 3. This lies in the first quadrant. Let's call this about, say there. alpha, and this is 1 add root 3I. X, and this is the y-axis. So there we have it. The modulus of this complex number is 2, and its argument, its principal argument, is pi over 3. Thanks for watching. I'm Alistair. Here's another trig ratio complex number. So again, we use a calculator to find out what cosine pi over 6 is. It's root 3 over 2. And sine pi over 6 is a half. So this is simplified as this times itself. When we close the brackets, we have 3 over 4 and root 3 over 4i and root 3 over 4i. So a quarter I squared. I squared is minus 1. So we have a 3/4 minus a quarter, which gives us 2/4, which is a half. So it's the real part, a half. Now we have two quantities of root 3 over 4, one here and another here, so it's 2. You can write this as 2 root 3 over 4i. Well, this cancels with this to give us root 3 over 2i. We can read off that the real part is a half and the imaginary part is a half root 3i. I'm Alistair. Thanks for watching. Hello there. Today I'd like to talk about properties of logarithms, and they have some very useful properties, and this is based on a definition of inverse functions of exponential functions. Now all of these are based on the fact that a is greater than 0 and a not equal to 1. So if we have here that the first property, a, is log to the base a 1 is equal to 0. This is saying if you raise a to the power of 0, our answer is 1. Some of you might be familiar with this, and if we have log to base a equal to 1, this is saying a raised to the power of 1 is a. Quite intuitive. Now b is for x greater than 0 and y greater than 0. So these two conditions must be satisfied for these two. Again, you might be familiar with this. Log to the base a of x, y can be written as log to the base a x and log to the base a of y. And the second is log to the base a x divided by y, log to the base a of x minus log to the base a of y. And lastly, c for x greater than 0 and the index p belonging to a set of real numbers, we have that log a to the base a x p can be written as p log to the base a x. Again, you're familiar with this one too. These are also very important, A, for simplifying equations. Thanks for watching this video. On the next two videos, I'll be doing a few questions using these properties. I'm Alistair. Hi there. The first four terms of a sequence are, as seen here, x over 3, x squared over 9, x cubed over 27, x to the 4th over 81, and so on. We need to write down the next two terms. As we can see, the powers of x are increasing as we go along, so the next one will be x to the 5th in the numerator. We have powers of 3 in the denominator, so we have 3 to the 1st power, 3 squared, 3 cubed, 3 to the 4th power, so we'll have 3 to the 5th power for the next one. We know 3 to the 4th power is 81, so 3 to the 5th power will be 81 times 3, which gives us 243. Oops, not there, but in the denominator. It's 243, so that's x to the 5th. And the next one will be x to the 6th power, which will be 3 raised to the power of 6, and that gives us 700, x to the 6, 729. Right, so those are two terms, x to the 5th over 243 and x to the 6th over 729. Just write them alongside here. So we have x to the 5th over, let's write that clearly, x to the 5th over 243 and x to the 6th over 729. Okay. Next, we need to write down a rule for generating this sequence. We have the base of x, and we have powers, ascending powers, starting at 1. So we'll call that n, natural number. And we have powers of 3. If you notice, the powers of 3 correspond to the powers of x. Here, the power of 3 is 1, the power of x is 1. Here, the power of 3 is 2, to give us 3 squared. And here we have the power of x is 2. Here it's 3 cubed. Power of x is 3. So we're raising the base of 3 to whatever n is in terms of the sequence. So for example, if we have, let's say, the 12th sequence, maybe x, sorry, it's 12th term in the sequence, x to the 12th over 3 raised to the power of 12. So this will be the 12th term in this sequence. Thanks for watching this video. I'm Alistair. Bye for now. Hello. Find the angles in the interval theta lying between 180, minus 180 degrees to 180 degrees. That satisfies tan 3 theta is equal to negative 3. Well, tan inverse of negative 3 will give us minus 71.5 degrees. So the principal value lies in the fourth quadrant, and the secondary value lies in the second quadrant. And this is what it looks like on the quadrant diagram. We have a minus 71.57 degrees. Remember, we're going between minus 180 to 180. And our secondary value is here at 108.43 degrees. So our general solution this is for phi, but remember, if you looked at my first video, phi is identical to 3 theta. So this is equal to minus 71.57 degrees at 180 degrees. But this implies, because phi is actually 3 theta, we just want to find for theta. So it implies that theta is equal to minus 23.86 degrees at 60 degrees. So we just divide here by 3. Now we need to have values of theta that lie between minus 180 to 180 degrees. So n, we need to have values of n that allows that. So n will start at minus 2, minus 1, 0, 1, 2, and 3. I've calculated values for theta, and you can check these by substituting for theta in the equation tan 3 theta is equal to negative 3, and you should get approximately negative 3 for each value of theta. So the first one that satisfies the equation is minus 143.86 degrees. Then we have minus 83.86. That's minus 23.86. 36.14. 96.14 degrees, and finally 156.14 degrees. Don't take my word for it. Check each value of theta to ensure that it satisfies the equation tan 3 theta is equal to negative 3. Thanks for watching this video. My name is Alistair, and I'll see you on the next one. Bye for now.